Hi, and thanks for joining the session today. I've been told I'm quite a fast speaker, so just please ask any questions during the session in the Q&A box below, and I'll also make a transcript available in there too. So today I'm going to be talking about using Wi-Fi to detect movements just from the air. So my name is Glenn Forbes, and I'm a PhD student from the Robert Gordon University and a part of the Data Lab's Industrial Doctorate Programme. I've been spending the last few years working with the Alban Housing Society on the next generation of smart housing, and today I just want to delve into one very exciting part of it. It sounds like sci-fi, but not only can we treat the air around us like an accelerometer, we can do it with incredibly low-cost tech that you probably already own. So let's just take a quick look at my demo. So I can't say it's my best angle, but it is a good demo. So I'm going to stand up from my chair and demonstrate completely wireless movement detection. The sensor isn't picking up my phone or any of the readings off of any sensors. It's simply using the Wi-Fi in the air. Now, as I stand up, you'll note that the graph moves up to 1 to indicate that I'm moving. And I'll keep there until I finish moving, just standing in the middle of the room. You'll see it drops down to 0. And as I start waving my arms around, it'll move back up to 1. And then I'm going to go walk around the room for a bit, and you'll see it stays up there, and it keeps the full duration of the movement captured. And then I'm going to go sit down, and that's going to drop back down to 0. You'll see it works even if I'm far away from the device or close to it. And there we go. So I think it's pretty cool, but I am a little bit biased. And what I want to do today is just give you an overview of how wireless sensing works and how we're using it specifically. So the underlying functionality that we're making use of is called channel state information. So radio devices communicating with each other, they transmit a set of measurements of how the signal changes as it travels from the transmitter to the receiver. And this means that we can extract an image of the path that the radio waves take. So this includes how they reflect off of different surfaces, travel through materials, and get blocked. Now that sounds very theoretical, so just to visualize this better, we can look at it in a more familiar context. So say we have a PC and a wireless access point, so like a router. And when these two devices communicate, they send frames to each other. Now for each of these frames, we get CSI at the receiving end. Now, some Wi-Fi devices can monitor traffic for all the frames being sent, and some can even be used to extract CSI for those. And so with that, we can estimate the wireless link between the monitoring device and any other one nearby. Now, we humans, we have a really strong impact on wireless signals. Because we're full of water, we're mostly opaque in the Wi-Fi domain. Now, this impact is so strong, in fact, that we can actually see it in our CSI data quite easily. Now, this diagram on the right here shows some CSI data I captured in my apartment. You can see the data is mostly consistent until about 11 seconds where it starts to get a little bit wobbly. Now, this is sustained all the way up until about 25 seconds where the signal becomes much more consistent. Now, as many of the data scientists among us will know, if we can see this easily in a graph, then surely we can get a computer to do it for us. And what can we do with that kind of information? So these are all common applications that we're seeing researchers demonstrate in the field right now. There's the movement detection, which I've demoed earlier. There are also been researchers experimenting with presence detection and even crowd counting. Others have been focused on vital signs estimation, so for instance, tracking the movement of your chest for breathing monitoring. And some have even been using gait to identify people for authentication. These are just incredible applications that we're seeing as the field matures. And if it's so impressive, then why isn't it more popular? And in short, it's because it's a little bit inaccessible. For a start, you're limited to using very specific sets of hardware, such as these ones listed here. And once you've got them set up and configured, the data that you produce has some pretty specific parsing requirements. So most of the software written for dealing with it is for use in MATLAB, which limits its usefulness from a data science perspective. And all of this requires a fairly strong base understanding of how Wi-Fi and the 802.11 specification works. To improve this situation, I've spent part of my PhD learning how some of these underlying systems work to produce a Python library which reduces a lot of this workload. Now, CSI-Kit, my library, allows many basic CSI functionalities such as parsing and processing and visualization all to be done within Python. It's designed to be easy to use and works with many of the standard machine learning toolkits such as TensorFlow and PyTorch. If this field interests you at all, I definitely encourage you to check it out on GitHub. Now let's quickly go through the broad strokes of the movement detection demo I showed you and how we're able to look at it from a data science perspective. So looking back at the example I showed earlier, it's clear that we can view this underlying wobbling pattern in the CSI sample when I was moving. However, in order to have our algorithm classify it, we need to quantify how wobbly the data is. And doing this, we'll not only know when the wobbling occurs, but we'll be able to tell the more wobbly bits from the less wobbly bits. Hopefully that's not too technical. We can use the Pearson correlation coefficient to measure the distance between CSI frames. And that gives us a nice number to measure with. And with one number, it should be easy to set a cutoff on how wobbly it needs to be for the movement to be tracked. In reality, this isn't really the case. In this example, along the bottom here, we can see that movement's been captured at the start and in the middle of this sample. And that's recovered with our movement detection algorithm. However, we can also see the correlation value for our CSI at the top here, along with a red threshold value set there. And we can see that this PCC fresh graph shows if we set the threshold there, that's the movement we'll pick up. Now, if we were to move this red line a bit further up to try and capture this movement at the start here, then unfortunately we're going to get all these false positives from this point here and here and here and here, which just don't occur in the movement detection algorithm. So instead, what we use is a threshold to determine whether there's movement in the data at all. And that's just one quick example of the challenges that we faced in interpreting this data. Solving many of these challenges, I've established a few tent poles which kind of set this up for a real-world application. First of all, we're using proportional thresholds, which allow for a continuous recalibration of the system as the environmental conditions change. Second, many of the data filtering approaches that are typically used require some kind of wind-up period to prepare the system. And with this implementation, that's not the case. All movement is captured, even if it's already happening when the system is turned on. Lastly, no matter how far or close you are from the sensor, the behavior is the same. It knows when you're moving and when you're not. So thanks for listening today. Let me know if you've got any additional questions, and know that I answer almost any email I receive as long as it's about my research. Thanks very much.